Here we go. This is going to be, what is this going to be? This is going to be Unit 11, 11.1. So, unlike Unit 10, Unit 10 was all about arc lengths and arc measures and kind of stuff around the outside of a circle. Unit 11 is going to be more about the stuff inside of the circle here. So just to start off with the first one, we've mentioned this one about 100,000 times now. We have a radius, right? So a radius is just going to be some segment inside of the circle where one of the endpoints is going to be at the center of the circle, and the other one is just somewhere along the edge of the circle, right? So a couple of examples here are going to be CF. And then even if you look on your notepad before you filled it out, all right, there is no segment here, but we can always draw one in. So segment CA would also be a radius, and then even CE would also be another radius. All right, now the new one, kind of this new definition that we have is a chord. So a chord is just going to be some segment on the inside of a circle where the endpoints, two endpoints, are just both going to be on the edge of the circle. So if you look at the picture, AB, point A is on the edge of a circle, point B is on the edge of a circle. Draw a line between those two, draw a segment between those two. You got a chord, right? Similarly, DF, there's no segment drawn in there. You could make your own segment. There you go. You have a chord. Now, if you want to think of a special kind of chord, we have the diameter. The diameter is a chord that passes through the center of a circle, right? And it's just made up of two radii, right? So if you look at CD, CD is a radius, CE is another radius. C, D, and E, those are all three collinear points. So you have those three collinear points. They are going to make up a diameter. All right, so DE is the diameter of the circle. So every single diameter is also a chord. But if you look down here, the biggest chord we can make in a circle is DE. Right? If you look at AB, that's obviously smaller than DE. DF, that's smaller than DE. DE is the biggest chord that we will be able to create inside of this circle. All right. So there's already, just one really kind of new term here. I don't know if we ever actually formally defined what a diameter is, but we've used it a few times. All right. Now, another new term here is we call this a secant. Okay, so a secant is a line. Very important that it is a line. All right, so remember a line goes on forever in both directions. All right, so it's going to intersect the circle in exactly 2 points. So a secant, if you take a secant, you kind of chop off the end pieces here, you do end up with a chord here, right? So if you look at just segment AB, and segment CD, those are just chords, right? But if you kind of extend them outwards, if you just go on forever in either direction, you're going to have line AB, and line CD are secants, right? So again, these very, subtle differences here, but they mean two totally different things, right? So a segment AB is a chord. Line AB is a secant. Right? And kind of the last new one here is going to be a tangent. So a tangent, again, is going to be a line, so it's going to go on forever in both directions, and it's going to be the same plane as a circle. So we're not going to be doing too much 3D stuff in this unit, so just think of everything as two-dimensional here. So a tangent is going to be a line in the same plane as a circle, and it's going to intersect the circle in exactly 1 point. All right, so if we were to look at this picture, line BC is going to be tangent to circle A at point B. All right, that point B, where the circle and the line intersect, that is where we call a point of tangency. All right, so just to kind of recap everything, I know we went through that a little bit fast. A tangent intersects a circle in one spot, whereas secants intersect a circle at two spots. All right, so both a secant and a tangent are lines, so they're going to go on forever. Tangent goes in one spot, secants go in two spots. Right? So those are going to be kind of the big, new vocab terms that we have in this, section so far. So now what we can do is let's just look at a few theorems that we can say about, these chords. All right. So here's what we have. We're going to have two circles here, and I forgot to write this on here, so I want you to assume that circle Q, remember we name circles based on that center point. I want you to assume that circle Q is congruent to circle T. All right. So if that's true, the circles are the same size. Here are two theorems that are always going to be true. All right. So if we have two chords in a circle, or let me start over. If we have two chords in a circle or in congruent circles, right? So they could either be in the same circle or just two congruent circles. It doesn't really matter. If those two chords are congruent, then the central angles that those chords kind of form with are also going to be congruent. All right, so if we want to just kind of zoom in on this picture, let's look at these two circles here. I have chord PR and I have chord SU, right? So this theorem says, hey, those two chords are going to be congruent. So what that means is these two central angles kind of associated with them are going to be congruent. So angle PQR is going to be congruent to angle STU. Right, so that's what that top theorem says. And it turns out the converse theorem, remember Q arrow P is kind of our converse. The converse is also true. So if you start with the central angles, if those two central angles are going to be congruent, then we can say the chords are also congruent. All right. Now, on the flip side of that, we can look at the arcs instead. So let's just look at the same two circles, and now let's just say the two arcs. So if we look in this picture here, let's go with arc PR. Let's say arc PR is congruent to arc SU. All right. So if arc PR is congruent to arc SU, then we can say the central angles are going to be congruent. And not only, oh, I actually made a mistake here. Yikes. So if two arcs in the circle are congruent, then their chords are congruent. So this right here should say, what should that say? PR is congruent to segment SU or chord SU. All right. So it turned, I guess I didn't need to cross that out. All right. So that is also true, but that's not what this theorem specifically says. All right. So if these two arcs are congruent, then their chords are going to be congruent. And similarly, the converse is also true. So if you start with the chords, you can end with the arcs. All right. So in other words, here, let's just zoom in and let's just write that down. Congruent arcs. All right. That is going to give us, well, actually here, let's use a biconditional. Right? We have that double arrow. We haven't used one of those since Unit 2. If we have congruent arcs, we have congruent chords, and we're also going to have congruent central angles. All right. So basically, these two theorems, right, we can use a transitive property and we can tie all of that together. All right, so let's just look down at this picture here. So we're saying radius OX, all right, radius OX is going to bisect that central angle, angle AOB. All right, so we just got to think, what does bisect mean? That's going to mean, we cut it equally in half. We cut it into two congruent pieces. So this alone, all right, that tells us angle AOX is congruent to angle BOX. All right, and these are central angles. Remember, central angles, that was a Unit 10 idea. That's just the center of our angle, or I'm sorry, the center of the circle is the vertex of the angle here. All right. So we have Congruent central angles. What can we conclude from this? Well, what do we get for free? Let's just look at the theorems above. So we know that AX, that's a chord, AX is going to be congruent to BX. Right, these are chords. All right. And the last one is arc AX is congruent to arc BX. All right. And we should really, I got to be careful on this. Let's put some segments over that, right? Because segment AX and arc AX, two very different things, but it's a subtle difference, right? This one's kind of that arch shape. This one's just a stick. All right. So that's everything we can conclude from this picture. All right. Two more theorems, and then we'll just work through some examples here. So, in a circle, all right, a radius that is perpendicular to a chord that is going to bisect the chord and its arc. Remember, bisect, that means it's going to go through a midpoint, cut it perfectly in half, however you want to look at that. So let's just look at this picture here. So we have this radius here. We can think of it as the diameter too. You could think of this as radius CO, or you could think of it as diameter CD. It doesn't really matter. They are telling us, hey, this guy is perpendicular to the radius. All right. So since it's perpendicular, we know that these two chords are congruent. We also know that this big arc right here, that is getting cut perfectly in half right here. So these two arcs are also going to be congruent, right? So if we had to summarize that, we could say if, in the context of this picture, if AB is perpendicular to OC, then we know AE is congruent to E. Uh-oh, another typo. That's not good. And now I can't erase. Why can I not erase this? AE is congruent to EB, and AC is congruent to CB. All right, next one. Within a circle or congruent circles, if we have a chord that is equidistant from the center, all right, so we are going to measure the distance from this chord, so like YM here, the distance from YN to the center of the circle L is just this distance VL. All right, so chords equidistant from the center are going to be congruent. And then the converse of that statement, congruent chords are equidistant. So if we look at this picture, YL is the distance from YM. I'm sorry. VL and YM. All right, YM is our chord. VL is the distance between those. This is going to be a 90-degree angle. Right, and this one is also going to be a 90-degree angle. Right? We could actually prove that these are congruent. Um, you're all probably saying don't do it, but I'm going to talk through it anyways because I can. We know that these are congruent because these are just radii, right? We're given that VL is congruent to LC, right? So how do I want to say this? We'll say VL is congruent to LC. This was given. All right. Those segments that we drew in here, LM is congruent to LN. All right, you got to think, why is that? Those are radii of the circle. All right. And then what we could do is we could prove that VM is congruent to NC. Uh-oh. V, see, now I lost my train of thought. VM is congruent to NC. All right. Anything, how can we do that one? This one is just Pythagorean theorem. All right. So it's going to get chopped perfectly in half by the theorem to the left. So we know that these two things are going to be congruent. So we could just double both sides and we're going to get that those are all the same, right? So this right here, this was kind of our proof. All right. See, that one's so bad. All right. A bunch of theorems on this page. So now let's just scroll down and let's work through some examples here. All right. So they want us to find AB. All right. So they want us to find this length here. Now, we have two chords, AB and QS. Those are equidistant from the center, right? So we know AB is congruent to QS. Right? How do we know that? Let's just say they're equidistant. Mhm. Since they're equidistant from the center, we know that this whole thing is congruent to this whole thing. So we've got a length of 14 down here. So we're going to have a length of 14 up here. So we'd say AB equals 14. Mhm. So that's one done. Now, this one is going to rely a little bit on Unit 10, just very, very little. Um, and if you look here, just kind of think about what can we 100% say for certain about this picture. We have two congruent chords. So if we have two congruent chords, that automatically means we have two congruent arcs. Right? So here's what I'm doing. I'm just going to throw some letters on this. All right, so I'll call this A, I'll call this B, I'll call this C. I went counterclockwise. That feels weird, but whatever. Um, so we know AC is congruent to CB. That tells us arc AC is congruent to arc CB. Right? So we have an X degree over here, so that means we can put an X degree over here because these two things are congruent. So now we could say X plus 102, right? That gives us the full circle. Well, that's just 360 degrees. All right, so we can solve that now. 2x plus 102 is 360. 2x equals, that's going to be 258. Therefore, x is going to equal 100. And, uh-oh, I don't have a calculator on me. 29, maybe? Okay, we're good. 129. All right, last one here. They want to know, hey, LV is perpendicular to YM. So it's that same picture from the theorem up top. LV is perpendicular to YM. All right. They're saying LV is 5, and then they're saying LM. Where's LM? LM is right here. That's 13. They want us to find YM. Our goal is to find this entire piece, right? So the first thing we should probably do is figure out that length right there. So I'm just gonna throw, how about an X? We're not using an X. I don't want to reuse any letters, right? So there's no X in this picture. So we're safe to just throw an X right here. So we can say X squared plus 5 squared equals 13 squared. All right, so just another Pythagorean theorem. This is actually a Pythagorean triple. We could get x equals 12. I'll let you work through that. We've done that a few times now. All right, so if x is 12, just double it, and that will give us ym. Ym equals 24. I really should have done that in pink, but that's okay. So ym is 24 because these two segments here are going to be congruent. All right, and that one's done. And I believe we just have two more. All right, sketch a circle R with a radius of length 5 squared of 3 and a chord xy that is 5 units from R. All right, so let's just start with circle R. Draw a perfect circle. Circle R right here. Um, it has a radius of 5 squared of 3 and a chord xy. We have to have a chord in here somewhere. So I'll just do that right here. We'll call this x, y. It's 5 units away from R. All right, so that, all that says is this distance here is a 5. All right. Now, the last thing I skipped over is the radius. We know the radius on this guy was 5 square root of 3. They want us to find the length of xy. So now this is very similar to the problem we just did. We are just going to use the Pythagorean theorem one more time here, and all we're going to have to do is double that length. Let me try not to repeat colors here. We'll call this side z. All right. So we know z squared plus 5 squared equals 5 square root of 3 all squared. Do not forget your parentheses on that when you type this into your calculator, right? Make sure you are, using those parentheses here. If you get, let's see, if you get 15 on this, you are typing that in incorrectly. You should get 75 for this thing right here. So we're going to have z squared plus 25 equals 75. Right, that's going to be 25 times 3, right? Remember, you square both of them. 25 and the square root of 3. 25 times 3 gives you that 75. Z squared equals 50. Just a z, square both sides. The square root of 50. And then simplify that radical. That simplifies down into 5. Square root of 2. All right. That is just this length, though. We need to find all of xy. So I shouldn't have circled z because that is not our final answer. We just need to double it. So xy, let's use pink, equals 5 square root of 2 plus 5 square root of 2. Just double it. It gives you 10 square root of 2. And yes, you could have just multiplied it by 2. It would have worked as well. All right. So that one's done. And now we have the dreaded word problem here. All right. So let's see what's going on here. We are designing a service tunnel to accommodate two trucks simultaneously. So think of this as like one of those tunnels running under Las Vegas. They got a bunch of tunnels going in right now. We want to accommodate two trucks simultaneously. If the tunnel can accommodate a width of 18 feet, what is the greatest height that the tunnel can accommodate? We need to subtract half a foot for fluctuations in the pavement. So like anytime they repave it, they're always putting a whole bunch of pavement down, and they got to flatten it out. So we need to whatever number we get, subtract 0.5 off of it, just to be safe. So, let's see what's going on here. We have a 6 foot, obviously we need a flat surface to drive on, so this right here is going to be 6 feet. They tell us the diameter is a 27 foot kind of tube, and we can accommodate 18 feet. We need to figure out how tall can this truck be. So here, I'm going to draw a new picture here because I don't really like what's going on in that one. All right, so we have a perfect circle once again. That's a little bit better. All right, so this is 6 feet. All right, what else do we know? The truck's corner, so this is going to accommodate 18 feet, and the whole thing is 17 feet across. Well, if it's 17 feet across, that means that this diameter here, well, the diameter is 27, so that means our radius is going to be half of that, which I believe is 13.5. All right, so if we think about these trucks, the trucks are 18 feet across, so that means that this right here is going to be 18 feet. So that means that this is 9 feet. All right. What are we trying to figure out here? What is the greatest truck height? Okay. So let's just think of this right here. These are going to be our two trucks, kind of like stacked together here. All right. So we need to figure out, well, what do we need to figure out? Let's figure out this length right here. Right? That is just right. We know we have a 6 foot depth there on our pavement. So I'm just going to do 13.5 minus 6. It's going to use 10.5. I think that's 7.5 right here. Right. And then what else do we need to figure out? Okay. We need to figure out this right here. So this is 9. This is going to be 13.5 as well. Let's figure out that piece right here. So we could say maybe x squared plus 9 squared equals 13.5 squared. All right, so we'll get a decimal on this one. I'm going to skip a few steps here. This video is getting kind of long. So 13.5 squared. I can already hear you guys complaining about how long this video is. 13.5 squared minus 9 squared. I got to take that. I need to square root it. That's going to be 10.06. All right. So what that tells us is this whole thing right here, we'll call this like y or something. Y equals 10.06 plus 7.5. All right. So that is going to be 17.56. Right? So that's how tall the truck can be. However, don't forget that last step. They said we need to subtract half a foot. So let's go 17.56 minus 0.5, which is 17.06. All right, so the truck must be less than 17.06 feet tall. All right. So anything taller than that, we're going to start scraping the sides of the tunnels and we're going to cause a cave-in. And we really don't want that. All right. There you go. That was section 11.1. Let's see here. How do I stop sharing? There we go. Sorry I couldn't be at school today, but I had a meeting. So, all right. See you guys later.